Hi, this is a proof of the central limit theorem that touches on the reason why the normal distribution probability density function is what it is, as well as on vectors, why the cross product geometric definition is equivalent to the algebraic definition. This proof took me quite some time to write down, to look through, to reflect on, and to understand. So I hope that by making this video, it will allow me to assimilate the content better and make the content mine. The proof is quite long. There are three parts to the proof. The crux of the proof is the second part, where you use what is known as a moment generating function. So the moment generating function is kind of like a fingerprint function. If you show that two different distributions have the same fingerprint, then you claim that the distributions are identical. So what we do in this case is we say that if you sample from a fixed distribution meaning that it's got a same mean, it's got the same variance, and it's with replacement, the distribution itself never changes. As long as you sample from a fixed distribution with a fixed mean and variance, you will converge towards the normal distribution function. So that's the central limit theorem. With replacement, sample mean fixed, sample variance fixed, as long as your sample size is large. So I didn't actually prove that it has to be more than or equal to 30. Some sources say 50. That's something which I haven't proved. I didn't have all the answers. I didn't prove everything, but I showed that n is large, that it converges to the normal distribution function. So let me talk you through the proof. I'll go through, it's quite in detail, it's quite detailed. I'll go through the first part where we look at sampling from a fixed distribution. Then I'll look at the fingerprinting function, and then I'll look at the fingerprinting function applied to the normal distribution. There are some supporting proofs that I'll talk about first. So uh, yeah, just these, actually only one of them in particular is required. And the others are uh, I suppose they are also required, but I'll talk about them after I talk about the main proof. So let's look at the first one. The variance of a multiplied by random variable x is a squared variance of x. Okay, so the first thing you do is you look at the definition of variance. Variance is the expectation of the standard deviation squared. And you apply ax in the place of x. So when you see x, you write ax. And then you consider the expectation of a multiplied by x. Because a is multiplied all the time by any variable x, you can factor out the same constant a and just look at the expectation of x and multiply it by a. Then you manipulate, you extract a squared, and the expectation of a squared multiplied by random variable, again you take out the a squared, and so you get the conclusion that variance of ax is a squared multiplied by the variance of x. Okay, so now let's look at the main proof. All right, so this is a bit detailed. Just be patient. I'll walk you through all the steps. First thing you do is you introduce standard score, which is the number of standard deviations that a random variable is away from the mean. And then you introduce the sum of standard scores, the sum of such random variables added together. And finally, you introduce the standard score of the sum per mean. So I will motivate why you divide by the square root of n. But if you divide by the square root of n, then you get this quantity, which I showed to you is equivalent to the standardized sum per mean. So the only difference is that the standard deviation has been divided by root n. And the reason for that I will explain to you later. Okay, so let's go through the proof proper. So first part, 2.1 is just a definition. 2.2 is expectation involving a constant and a random variable. So you pull out the constant. Then you take the expectation of two variables summed together, and that is separately the expectation of each variable summed together. So expectation of x sub I is mu. So mu sub mu subtracted from mu is 0. And so the expectation of y sub I is 0. So for all of these three things that we look at, the standard score, the sum of standard scores, and then the standard score, the sample mean, we'll look at the expectation and the variance. Okay, so let's look at the variance of y sub I. So you pull out the constant and you square it, as we demonstrated in the proof, the supporting proof. Then the variance of two variables added together is the variance of each variable added together. And you don't subtract, you add, because the variance of one can be combined with the variance of the other to get a higher amount of variance. Is that obvious? I think that that's obvious. If you want me to prove that, let me know. And I'll think of a more rigorous way to define it. So you get variance of a constant, which is 0. So you just have variance of x sub I. The variance of x sub I is the population variance. So you get population variance divided by itself, and you get 1. Okay, so the mean, the expectation is 0, and the variance is 1 for the standard score. Let's look at the second part. So here you're looking at the sum of standard scores. Let's look at the expectation first. So the expectation of the sum is the sum of the expectation. Okay, why is that true? Well, consider the middle term. If the middle term was considered alone, the sum of y sub I, that would be equal to n times mu, where mu is the sum of is the mean of the standard score. It's not the population mean. So if you sum up the mean n times, you will get the sum of all of y sub I. And the right hand side, if you summed up the mean, you would also get n times the mean of the standard score. So these two are equivalent. So you can swap the operations as they are commutative. So ask the question, what is the expectation of y sub I? But you've shown that previously to be 0. So you're summing up 0 and you get 0. Okay, so that's the expectation of the sum of standard score. Let's look at the variance. So the variance of a sum is the sum of the variance, because each of the individual terms' variance will be added to contribute to the total variance. The maximum variance you could have is the sum of the variance from each of the components that you're adding. The variance of y sub I was previously shown to be 1. So you're adding 1 to itself n times, and therefore the variance of the sum of standard scores is n. Okay, so let's look at the last one, the standard score of the sample mean. Alright, so if you rationalize the denominator, you will get square root n on top. Then you define S as the sum of the standard scores. Remember what S stands for? And by definition, that is this expression, the number of standard deviations that you are away from the mean. Then you extract the constant from the sum, and then you sum up individually both terms. So a constant added to itself n times is n times the constant. Then you distribute 1 over n, so the n cancels out. And by definition, this quantity is x bar, the sum of x sub I over n. So you recover this useful expression, which I have to demonstrate to you is in fact the standard score, the sample mean. So it looks very similar to the previous definition, except now that the standard deviation has been divided by root n. So to explain why that is the case, I'll look at this Wikipedia article, standard score. And what it shows is that the variance of x bar, by definition x bar is sum of x sub I divided by n, extract the constant 1 over n squared, take the variance of x sub I added to itself n times, that is n times the variance, n times, n times the variance, divided by n squared, so you get variance divided by n. Yeah, so that's the variance of the sample mean. And if you take the standard deviation, you square root it, and so you get a square root of n term. And that is why this standard score of the sample mean has a diversion by square root n, because this is the standard deviation of the sample mean. Okay, so that's that. Let's look at the expectation and the variance. So by definition, the expectation, you pull out the constant. The expectation of the sum, of the sum of the standard scores is shown to be 0, right? And the variance is shown to be 1. Oh, sorry, n. The variance is n. The expectation is 0. So the expectation is 0, and the variance, you pull out the constant, you square it. You take the variance of the sum of the standard scores, that's n. You simplify, n squared over n squared is 1. Okay, so we got through the most technical bit, I think. Now just look at the MGF, the fingerprinting function. Okay, so what is MGF? Well, MGF is expectation of e raised to t y sub I, or if you choose x later, then or z, then e raised to the power zt, or if it, yeah. So the purpose of using this moment generating function is because when the dust settles and you look at the logarithm of the fingerprinting function, you will show that as n goes to infinity, as you sample more and more, uh, as your sample size grows, your sample mean fingerprinted would converge towards t squared over 2. And t squared over 2 is also the moment generating function of the normal distribution, standardized. So the MGFs of unique variables, random variables, are unique. Okay, so that's the motivation for why we're doing it. Let's now do it and step through it. Okay, so the first part is by definition of the Maclaurin series of e to the x. Remember, x to the n over n factorial, sum from 0 to infinity. Then the second part is you write down t y sub I in the place of x. Then you apply the expectation to the random variable, so y sub I, and the rest are the constants that you factor out from the expectation. So you extract them. Then remember that the expectation of y sub I is 0, and then you have this expectation of y sub I squared. But you have to remember that the variance of x is expectation of x squared minus the squared expectation of x. Let me prove that to you, and then I'll come back to this. Okay, so the way you prove this is you factor out you define it first. So expectation is 1 over n and the sum of all such terms. Then you expand special form. Then you take the sum and you apply it to each of these terms. This is a constant, so you get n mu squared. If you sum out x sub I, you get n mu. Simplify. And by definition, this is expectation of x squared, and the mean is expectation of x quantity squared. So that's the proof. Okay, so what you do is you isolate expectation of x squared. Make this the subject. So you bring this to the right. So you get variance of y sub I plus expectation of y sub I quantity squared. And you already know what these values are. The variance of y sub I is 1, and the expectation of y sub I is 0. So you can simplify further, and you get this expression. Okay, so this is just the MGF of the standard score. Now we're going to look at the MGF of the sum of standard scores and the MGF of the sample mean standardized. Okay, So remember, the objective is to show that the fingerprint of the sample mean standardized is the same as the standard normal distribution. So that's why we eventually have to get the fingerprint of the standard score of the sample mean standardized. Okay, so first let's look at the MGF, the fingerprint of the sum of standard scores. So the sum of standard scores by definition is when you add up y sub I all the way up to y sub n, however many standard scores you are adding, there are n such standard scores. You use the property of indices to separate this into individual terms. The expectation of a product is the expectation of each individual term multiplied together. That is obvious in the case where the terms are all independent. And because you're sampling from a fixed distribution and with replacement, the result that you get in one particular sample is independent of the other samples. Or I'm sorry, the result that you get in one particular sample item is independent of the others that you are also sampling. But there's a different definition of the word sample. So the sample here just means take one rather than take n. Okay. So you get the product of these terms from I equal 1 to n. And by definition, the expectation of e to the t y sub I is just the MGF of y sub I with argument t. So you're going to multiply it by itself n times. They're all identical, right? And therefore, you take the result that you got from the previous case, and you just raise it to power n. Okay, finally, we now get to the fingerprint of the standardized sample means. So the only difference between the sum of standard scores and the standardized sum of standardized sample mean is this term square root n. So square root n is included as the in the argument, and square root n consequently appears in all these terms. Instead of writing t, you write t divided by square root n, and you square it, and then you raise it to power n. Okay, finally, as promised, this is the Maclaurin series now, the final adjustment to the fingerprint to make it easy to read. So you take the logarithm of this whole term added terms, which looks quite it's not that bad actually. There's only 1, 2, 3 of them, but you add them all out, and you recognize this as 1 plus x, ln of 1 plus x. Right? So I use another Maclaurin series, and this is the form. So here you treat the whole term as x, the whole expression as x. Then you apply the form that you generalized from the sum of ln of 1 plus x. So you have k, and then you have -1 to the k plus 1, and then you have x to the k. So here the whole thing is x, and you raise it to the kth power. Okay, so what you do is you separate the sum from 1 to infinity to the case where k is 1, and then the remaining terms from k is 2 to infinity. So from 2 to infinity, it looks exactly the same. And when k is 1, you get 1 plus 1 is 2, minus 1 squared is 1, 1 divided by k is 1, so 1 divided by 1 is 1. So you just have these terms here. Okay, then you distribute n, because you multiply everything by n. So if you multiply throughout by n, the first term, n will vanish. And for all subsequent terms, you'll minus n. So minus 2 over 2 is minus 1. So you're minusing n. Okay, and now you apply the conclusion, which is that if n goes to infinity, all these terms will vanish, and you're left with just the leading term, which doesn't have n. And you're going to show now that the MGF, or the standard normal distribution random variable, is in fact the same fingerprint. It has the same fingerprint. And therefore, the two MGFs match, the fingerprint matches, may take the logarithm. And therefore, the functions, the functions that are fingerprinted are the same. And hence you conclude, if you sample from fixed distribution with replacement, the sample mean when standardized will converge towards the standard normal distribution. Okay, so I think we've done most of the work. Now we just get to the MGF of the normal distribution. Okay. Oh, and I'll just talk about this at the end. So I'll come back to this too later. Okay, so now the MGF of the normal distribution. All right. So by definition, MGF is an expectation Tx, right? E to the Tx. Expectation means you multiply by the probability over all possible values that x can take from minus infinity to infinity. If x is continuous, you take the integration of this with respect to x. Okay, so what is the probability density function of the normal distribution? So we're checking normal distribution, a standard normal distribution actually, but first we just look at normal distribution. So it has this form, and we're going to show that if you use this form, you get the same fingerprint when you take logarithm. So we apply what we are initially checking. So we haven't shown that it's this, but we'll show later that it has the same fingerprint and therefore it's this. Pull out the constant, combine the two terms, then standardize it, set the mean to 0 and the standard deviation to 1. Then replace x with z, because z represents the standard score. So you get this result. Then complete the square. You complete the square. So you take the term with zt and divide it by 2. And then you subtract the additional term that you've added. Right? And you take the special form of this. So you remove it. Okay, so you pull out the term that doesn't include z, and you get this result. So all you have to do now is it the same? Yeah, so I should have mentioned this previously. If the logarithm of the fingerprint function converges to this, then the fingerprint function itself without the logarithm is just e raised to what you get previously. So you show that the moment generating function is this. So you use the logarithm to recognize that in the limiting case when n goes to infinity has this fingerprint in the logarithm, and therefore the MGF has this fingerprint. So all we have to do now is prove that if you integrate this, you get square root 2 pi. If you can show that if you integrate this, you get square root 2 pi, then you've shown that they have the same fingerprint. And therefore, the probability density function that we assume is the necessary probability density function. So it is necessary, it is sufficient, it is unique, if you can show that the integration of this is square root 2 pi. So let's do that. Okay. All right. So to do that, I'll do two things. First, I'll prove that if you integrate what is known as the Gaussian integral, you'll get 1 over square root pi. Is that correct? Oh, I made a mistake. Yeah, this is a mistake. It should say root pi. So this should be root pi. And this should be square root of 2 pi. Okay, I just realized that. Right. So the Gaussian integral, this integral, you convert coordinates to a polar coordinate. So initially it's just this expression squared, and this expression is a dummy variable x. You can replace it with a dummy variable y, and then you can combine the integration into dx dy. Then you convert to polar coordinates r and theta instead of dx dy, and I'll motivate the reason for why you have a factor of r. If you accept for now that you introduce r, you simplify with the substitution s is equal to negative r squared, negative, so you swap the limits of the integration and you make it negative. Then you integrate e to the s ds, and that's just e to the s. Substitute 0 and minus infinity, 0 and minus infinity. So e to the minus infinity is 1 over e to the infinity, which is 0, and e to the 0 is 1, multiplied by pi, and so therefore you get pi. Okay. I haven't shown why you introduce r. I'll show that to you later. And then you have the second part. The second part is proving that this thing is square root 2 pi. So it's very easy to do that. You just see that it's shifted by t units to the right. And if you shift it to the right t units, the area under the curve doesn't change. And then you scale it. So how much do you scale it by? Well, what you do is you make it so that the square is applied to 1 over square root 2. So you're looking at x squared in one case, and you're looking at 1 over square root 2 multiplied by the random variable that's translated. Translation is irrelevant because it doesn't change the area under the curve. Scaling factor is 1 over square root 2. So you multiply throughout the graph by square root 2. So therefore, the area is square root 2 pi. Okay, so now all I have to do now is show you that you have to introduce r. Okay, so to introduce r, the reason for it, the short answer is because of Jacobian. But I have to motivate why you introduce a Jacobian. So this is how you derive the Jacobian. What you do is you look at an area initially treated in the variables v and u. So in our case, r and theta. And then you look at how that maps to the same area expressed in terms of x and y. So when you express it in terms of different variables, the coordinates may shift and you may get a different shape, but you're arguing that the area should be the same. So this comes from Larson. Larson is very elegant, but perhaps it's not very accessible. So I also looked at Stewart. I'll look at Larson first though. So in Larson, all you have to do is find the two vectors that define the area of the parallelogram. They assume it was a parallelogram. Is it necessarily a parallelogram? Yes, because when you transform the same direction vectors, they'll point in the same directions. So it will be a parallelogram. So you're looking at how the vector changes as you change u and as you change v. So from m to n, you describe it in terms of two functions, g and y, when g and y themselves are functions of u and v. Right? So for mn, you're changing only u, right? You only change u. So you look at how uh, the terms x and y change as you change u. Hmm. Right? Because you define uh, mn as the function g applied to the I component and the function h applied to the j component. And then Uh, and then by definition, the function g is the limit of dg du because you're changing only u. Is this obvious? Okay, I agree with the first line where you say that mn is in terms of the function g and h. But why the difference? Well, because you take g initially, and then you take g at the end, and you take the difference in g, and you apply that to the variable I. So as you change u, the ith component will change. As you change v, the jth component will change. But is it obvious to me that only changes in g will affect I, and only changes in h will affect j? I suppose we must treat I and j as u and v initially. Yeah, if we treat I and j as u and v initially, then I think it's obvious that the second line follows. Then you have the change in g multiplied by the amount that you change by u, and then in the ith component. And similarly for the change in h multiplied by the amount that you change in the h direction, in u direction, and the h component, the jth component. Yeah. Oh, no, I made a mistake. It should be the change in h. The change in h, when you change just u and the jth component. Oh, sorry, I misunderstood it. Okay. So g and h are both functions of u and v, but g can change with respect to u, and h can change with respect to u. And initially, you're just looking at how g and h change with respect to u. So h affects the component in the vertical direction, and g affects the component in the horizontal direction. And that is why you apply I and j, because you're saying as g changes, only the horizontal component will change, and as h changes, only the vertical component will change. And initially, you're looking at just what happens when you change just the horizontal component. So del u. Is that the best way to express it? So let me state it again for the record. So your x and y components are functions of g in terms of u and v, and h in terms of u and v. But g affects only the x component, and h affects only the y component. So initially, you're looking at how this vector changes in its mapping as you change only the horizontal component, only u. So initially you change only u, right? And you look at how the corresponding components g and h change, and therefore how it changes in its horizontal and vertical description. Yeah, okay, I think that's the correct way to state it for the record. Right. So by definition, the change in g is del x del u. Is that obvious? Yes, because you define g to change only x. So del g del u becomes del x del u, and del h del u becomes, by definition, del y del u. So that's mn. And you can do the same thing for mq, except that mq will be with respect to v. Yeah. So if you find the area of the parallelogram, that would be the cross product of mn times mq. So I haven't shown to you yet that the area is equal to the cross product. I will demonstrate that to you after this. But when you show that the cross product is the area, you notice here they are taking 3 dimensions. We are looking at only 2-dimensional case. So our third dimension is just the null vector, 0, 0. uh, if you take the determinant, you would remember the way you take the sign minus and you expand this in cofactor expansion. So you'll cross with 0, and then you'll cross with 0, make it negative, still 0, and then you get a term involving k. And so voila, you have shown that the area has a Jacobian as well as the new coordinates uh, multiplied together. And that's why your dA involves the Jacobian. Okay, so I will show you that the Jacobian in the case of polar coordinates involves an r, right? So x is r cos theta, y is r sine theta. Remember the unit circle definitions, how you find the coordinates x and y when the unit circle is expanded and scaled to r. Take the derivative with respect to r, you get cos theta. Take the derivative with respect to theta, you get negative sine theta times r. Do the same for y. Then take the determinant. So you get r cos squared plus r sine squared. Cos squared plus sine squared, remember the Pythagorean identity is equal to 1. So the Jacobian for the polar coordinates case involves r. So we've shown that, but our demonstration requires that you accept that the cross product is the area of the parallelogram. So let me demonstrate to you why that is the case. Hmm. So I'm thinking about whether I should tell you about the demonstration and do it. I don't think it's necessary. Let me see whether I have to. I've mentioned this, yeah. Uh, hmm. No, I don't think it's necessary. I think I've mentioned it. Okay. So let's look at the reason why the cross product is the area of the parallelogram. So from Wikipedia, uh, they use this example where the arrow is slanting to the right. It doesn't look at a case where the theta is obtuse and the arrow slants to the left, but in the special case where you slant to the right, if you take b sine theta, you will get the height, and the height multiplied by the length is the area of the parallelogram. So let me show to you that the determinant does give you the same thing as the geometric definition. And then the geometric definition I've shown to you in the special case where theta is acute is in fact the area. So I guess I could improve this video. I could show you that it's true also in the obtuse case. I haven't thought of that. If you can come up with a proof that involves the obtuse angle, I'm very interested to see how you do it. Okay, so to show that they are equivalent, what you do is you first take the cross product of two vectors in 3 dimensions, and you define the dot product as involving the projection. Then you square it. Remember, when you square it, you dot it with itself. Right? So each individual component is squared. So if you take A cross B and you square it, you'll take this vector and you'll square all of the individual components, which if you simplify and by expanding the special form identities, you get this result. It looks very messy, but remember this part over here. Then if you take the dot product of a vector with itself, you will get this result. And this part matches with this part. So if you add the cross product squared to the dot product, this term will vanish because here it's positive and here it's negative. And you'll be left with just these terms. And these terms are a1 squared plus a2 squared plus a3 squared, which is vector a squared, multiplied by b1 squared plus b2 squared plus b3 squared, which is vector b squared. So you say therefore, you make this the subject. This is therefore mod a squared mod b squared 1 minus cos squared theta. And 1 minus cos squared theta by the Pythagorean identity is sine theta. squared. When you take the square root, A cross B is therefore mod A mod B sine theta. I got this proof from Khan Academy. Yeah. Okay, so I've shown to you that their magnitudes are the same. And so I've demonstrated that in the special case where theta is acute, you can just take the area of the parallelogram. And I think the parallelogram that they drew is when theta is obtuse. So I have not shown it in the obtuse case. So it's not complete. I would be very grateful if someone can show me why it is true in the obtuse case. But I'll tell you one last thing, which is not really important here, but is good for completeness. And that is the right-hand rule. So you can motivate the right-hand rule as well. You take the cross product of A and B. Then you look at the component of A cross B. So that component, the z component, which tells you the direction of the vector that you get as a result of the cross product, is the last term, right? A1 B2 minus A2 B1. And remember what A1 and B2 represent. A1 is the component in the x coordinate, and B2 is the component of B in the y coordinate. So thinking of the unit circle scaled by some length A, you get A cos alpha, right? And for B2, you get B sine beta, where alpha and beta are the angles that you've rotated the vectors A and B by. Then you recognize the identity as the addition identity. And then you get sine beta minus alpha. So if you have alpha and beta, remember your hand points along alpha first, your right hand. Your fingers point along alpha. Your non-thumb fingers point along alpha. Then they sweep to point along beta, and your thumb points up. And the reason for that is because if you take sine of beta minus alpha, and when beta minus alpha is positive in the first quadrant, you get a positive number. Whereas if B is rotated to be on the right of alpha, um, then your non-thumb fingers point along A first, then they sweep towards B, and your thumb points down. Because if you take beta minus alpha, it will become negative, and if beta minus alpha is acute, sign of that quantity is negative. Yep. So that's all I have to say about this central limit theorem for now. Oh wait, there's one last part, right? So I showed you that if you take the fixed distribution with replacement and you sample repeatedly from it, as your sample size goes to infinity, you will converge the same fingerprint as the standard normal distribution. And I argue that because the MGFs of unique variables are unique, therefore if they have the same fingerprint, they would be the same distribution. And therefore, your sample means standardized will converge towards the standard normal distribution as n goes to infinity. But what about the case where you're just looking at sample mean, not standardized? Well, in that case, you will scale just by sigma and shift by mu, so it's still normally distributed. And in the case where you're just looking at the sum of variables, you'll just scale by the factor 1 over n, because you multiply throughout by n, and it's therefore still normally distributed, because you're just scaling a normal distribution by some factor. And in the other case, you're just shifting it by another factor. Yep, so that's all I have to say for central limit theorem. And as a bonus, we talked about the vector product, the cross product. Yeah, so if someone can give me feedback on why it is true that the area of a parallelogram, in the case where the angle is obtuse, is in fact the cross product, I would be very grateful. Yeah, thanks.